Good evening, everyone. I'm Banduka, Technical Events Coordinator for Civil Engineering Sectional Committee. And today is the 16th session of this lecture series. Our lecture series on lightweight hybrid multi-story construction technology for houses and apartment buildings. So we are very grateful for our resource person Professor Tisan Jayasinghe, for conducting this lecture series so far. And we have gained a lot about this cost-effective technology for houses and apartment buildings. Thank you very much, sir, for that. And over to you, sir. So I think sir is muted.
Can you hear me now?
Yes, yes. Yes, sir. Now we can.
Sorry about that. Okay. So, good evening, everybody. So, we talked a little about masonry design part of lightweight hybrid multi-story construction last time. So, today I'm planning to give more details about the masonry design part of it. So, if you look at the example that we have considered a house of this type of shape. So this is the living area, and these are the rooms like kitchen, pantry, bedrooms, and so on. So what I proposed was that since we can have L-shaped columns at these places, what I proposed was to run the concrete beams in this direction. So that we'll be able to run the supporting beams this direction, and these can be about 4 meters, and this direction it can be any amount, can be 3.5 to 4 meters, and if you want you can have even larger spans like 6 meters. So when you look at these, you can see there is no restrictions as such. You can have any size that you like, and so these are the masonry walls, and masonry walls will be carrying the load of a concrete slab spanning about 2 meters. So the span will be 2 meters. Span will be 2 meters. So you can see that the masonry wall will carry the weight of these slabs, and in doing so, we are transferring about half the load onto the concrete beam, half the load onto the masonry wall. Because we are transferring part of the load, we can minimize the amount of reinforcement needed in the beams, because reinforcement is very expensive these days. It's useful to have minimum reinforcement in the beams. So that is one advantage. So now the question is, how are you going to design the masonry wall? So if you look at the scenario, we have a masonry wall. Not a thick wall. We have considered 150 millimeter block wall, and the masonry, the concrete beam will come and rest on it. The slabs will be resting on it, on these hollow blocks, and then we finish it to a thickness of about 90 millimeters. So if you consider the width that will contribute to this load, it's about 2 meters. The width that will contribute to the load is about 2 meters. So now this will allow us to do some calculations pertaining to the concrete slab and the masonry wall. So the first thing is, what is the load from the slab? And it is given by 1.35 GK plus 1.5. And this value will be the weight of the slab, which is 0.09 into 25, plus we can allow about 1.0 for finishers. So if we allow that into 1.35 plus 1.5 times an impulse load of around 1.5, and this will give us a value like 0.09
6.63, sir.
6.63. So let's say it's approximately equal to 6.7 kilonewtons per meter. So we get this is the load that is coming from the slab, and since we are having a 2 meter width, the total load will be 2 times 6.7 kilonewtons per meter. Now, in addition to that, we have to consider the self weight of the wall. Now, for the self weight of the wall, I'll consider that this wall has a height of 3 meters. So the self weight of the wall will be 0.15 into 12. The density of hollow blocks is 12 kilonewtons per meter cube. Plus, if we assume that we are going to have a plaster, the whole idea of this use of high quality block work is to avoid the plaster. So, but still we'll assume that we are going to get a plaster of 15 millimeter thickness on either side of a density of 20 into 1.35. And we have to multiply that by the height of the wall as well. So the answer is 0.15 into 12 plus 0.03 into 20 multiplied by 1.35 multiplied by 3 meters. So you get 9.7. Is that right, Mandu?
Yes, that is correct, sir.
Yeah, that's correct. 9.7. Now this will allow us to look at it in a proper context. So we are getting a load of, if you consider one masonry wall of 3.0 meter height, we are getting a load of 13.4 kilonewtons per meter from the slab, and it has a self weight of 9.72 kilonewtons per. So if you look at the total stress per flow, that is 13.4 plus 9.72 divided by 0.1. So that gives 13.4 plus 9.72 divided by 0.1. So that gives a stress of 154 kilonewtons per square. So that is the stress, and you can see it's not a extremely high stress, because when you convert it to newtons per millimeter squared, what you get is 0.154 newtons per millimeter squared. So that's a value. So let's look at it from the masonry design point of view. So in masonry design, the first thing is we have to see what is the type of connection we get. We are getting a concrete slab supported by the masonry. So we have a height 3 meters, but we have to find what is the effective height. So when masonry is supporting other elements, we can have different effective heights. So that is one of the problems that we have. So what are the other problems we have? Now here you can see we are having a symmetric arrangement. So the eccentricity at the top will be very small. Then we also have to consider the initial eccentricity. So there's a small value, and so we'll find that also. Then in addition to that, there's a tendency for this to buckle. Tendency for the masonry wall to buckle. That also has to be taken into account. That means, we have to see what is the capacity reduction factor to be considered to allow for buckling. That means, we are going to say we are going to have a slightly lesser capacity. And then the other parameter that we have to look at is what is the partial factor for material strength. In concrete we use 1.5, but in masonry we use higher values to allow for variations in quality variation to work and construction. So now let's see how to find these parameters for masonry design. So I'm going to share the screen now. This is the masonry node that I showed you last time. Just one moment. This is the masonry node I showed you last time. And when you consider the type of blocks, we are using hollow blocks. So we may be in this category. So we are type of two-way blocks. Two-way blocks. And the mortar that we use is M4 mortar, giving a strength of 4 newtons per millimeter squared at 28 days. So the strength is given by K is equal to K times FB to the power alpha, Fm to the power beta. And if you look at the value of K, it is 0.524 group 2 constructed with general purpose motor. K is 0.5. And I told you that, we have to go for high quality block work. So we can easily obtain blocks of 5 newtons per millimeter squared or above in Sri Lanka, provided that you purchase it from a quality manufacturer. So if you look at alpha and beta values, alpha is 0.7, beta is 0.3. So we can actually calculate the characteristic strength of the masonry, by using this equation that we did last time. So if I stop share, now you can see the characteristic strength of compressive strength of masonry is going to be 0.52 times 5 to the power 0.7, 4 to the power 0.3. Yeah, I'm assuming that we are going to use 5 megapascal crushing strength blocks. That is practically possible to manufacture in Sri Lanka. It's possible to purchase as well. So there are few quality block manufacturers in Sri Lanka and they provide this kind of strength. So the characteristic strength that we get is the advantage of Eurocode, because it straight away gives an equation that allow us to calculate the strength of masonry multiplied by 4 into so this comes to 2.43 newtons per millimeter square. So that is one of the problems that we wanted to solve. Now I'm going to share the screen again. So if you look at another parameter, an important parameter, is that when the state of direct or flexural compression unreinforced masonry made with units of category 2, we can have 2 gamma m values. And the important thing about load bearing construction is you have to do the construction properly with reasonable quality control. And so we can use, if you want, you can use 2.6. The worst case is 3. So I'll assume gamma m is 3. I'll assume that gamma m is 3. So that means if you look at the overall factor of safety, we are multiplying the loads by 1.35 and 1 GK and 1.5. So if the average value is 1.4. So we have increased the loads by 1.40%, and we are dividing the strength by 3. So the overall factor of safety is 3 into 1.4. So it's over 4. So the overall factor of safety that you are going to get in masonry design is, you can see, gamma m is 3, and this value is 1.4. 3 into 1.4 is over 4. So we are going to get a overall factor of safety of more than 4. More than 4. So that means, you know, there's a significant factor of safety. So there's nothing much to worry, right? So let's see. Then if you know the characteristic strength, then the design strength will be Fk over gamma m. So that will be 2.43 divided by 3. So it comes to 0.8. So we have a design strength of 0.81 newtons per millimeter square. Then the next important question is, what is the slenderness effect? What is the slenderness effect? For that, you have to see, I'll share the screen with a different note. The second part of the note, and it tells you how to do the design and with examples. So after the lecture, I'll share these notes with you. I'll share it with Bandhuka so that Bandhuka can share with all of you.
Okay.
Right. So basically, you can see reinforced concrete slabs spanning onto the wall from both sides. The effective height, H effective, is given by rho n times H. So here rho 2 is applicable. So the effective height is 0.75 times the height. Effective height is 0.75 times. So that can be sorted out. And then the masonry codes allow us to increase the thickness, but I generally don't use that, because that means you have to provide piers and all kinds of other return walls and so on. So that can be too restrictive. So you can see the maximum slenderness ratio is HEF divided by TEF, and should not be greater than 27. Should not be greater than 27. So if we consider our case will be, so we can calculate the slenderness ratio. And this is a calculation that you have to do when the loads from both sides are not equal. But here in our case, it's symmetrically loaded, so you don't have to really worry about this lengthy calculation to find the eccentricity at the top of the wall, because the eccentricity at the top of the wall is 0. We are having similar spans on either side of the masonry wall, so that is not a major problem. And the initial eccentricity is given as effective height divided by 400. So that is a nominal eccentricity that is taken into account to allow for construction imperfections. So we allow a small eccentricity, but if it is less than or equal to 0.05 t, then it says the capacity reduction factor is taken as 0.9. Capacity reduction factor 5 for the load capacity is taken as 0.9, but we have to see where we stand on that account. So we have those information. Now let's see, with the available information, let's do few more calculations. So now we know the slenderness effect. So slenderness effect, we have to find the slenderness ratio. That is effective height 0.75 times 3000 divided by 150. So this comes to 0.75 times 3000 divided by 150 comes to 50. It comes to 50. So the slenderness ratio is 50. Slenderness ratio is 15. Slenderness ratio is 15. So the slenderness ratio is 15. Then also we have to see what is the initial eccentricity. And that is 0.75 into 3000 effective height divided by 450. So it's 5 millimeters. And 0.05 t is equal to 0.05 into 150. So that is 7.5 millimeters. So this initial eccentricity is less than 0.05 t. So now we can see we have a slenderness ratio of 15. So let's see what is the effect of eccentricity. So eccentricity at the top is 0 and mid height we don't know, that we have to find, and here also see. So we have to see. So the eccentricity at the bottom, so in the middle, is given by a complicated equation, but they have given a chart. So here you can see the initial eccentricity is less than 7.5 millimeters. It's 5 millimeters. So we have to go on the basis of this chart, which is applicable to 0.05 eccentricity. So if you go by that chart, then you can see as the height increases, the slenderness effects grow, and when the HEF over TEF ratio is 15, the corresponding value is 0.7. So that means we have a capacity reduction factor 5m given by 0.7. So we have a capacity reduction factor of 0.75. So that means although we have a design strength of 0.81 newtons per millimeter squared, to allow for slenderness effects, we have to multiply it by 0.75. So it comes to 0.81 multiplied by 0.75. So it comes to 0.6061 newtons per millimeter. So it comes to 0.61 newtons per millimeter squared. And from one flow, you can see we have calculated earlier the stress per flow comes to 0.154. Stress per flow is 0.154. So that means, it's only 1/4 of this value. That indicates so this indicates can go up to number of flows. So we can have a situation here we have one flow, another flow, another flow, and each one of these will give a stress of 0.15, 0.15, 0.15. So the total will be 0.45. So that means if you want, we can go for another flow as well. And these with an overall factor of safety of 4.2. Overall factor of safety of 4.2. So you can see there's a good possibility to complete the walls with a wall thickness of 150 millimeters and still have a factor of safety of over 4.2, provided we place the concrete slabs on the wall directly and make it continuous so that each slab will span 2 meters, providing a load of 1.0 meter width onto this. So the whole idea is share the loads. Number 2, minimize slab loads. See, use hollow blocks out of concrete, chip concrete, so that we use less materials. We get high strength. So when you do all this, you can see the wall thickness can be reduced to 150 with significant savings on the wall construction, and also it's possible to go up to about 4 floors without, while having an overall factor of safety of about 4 for masonry. Is that clear, Bandhuka?
Yes, that is clear, sir.
That's clear, right? So basically, you can see there's no risk even up to 4 floors, though the wall thickness is only 150, and you can support this lightweight system up to 4 floors. So any apartment building having up to 4 floors, this method may be feasible, because our idea is minimize the amount of concrete in the slabs, minimize the amount of material in the structure. Then comes another question, because these days we have the climate change, and many people like flat roofs. So if you like a flat roof, what is the arrangement possible? If you have a flat roof, it's ideal to have a lintel and then have a bitumen sheet and then support the slab and make it continuous. And on this side is supported on the beam. So earlier I showed you that the beam can be designed as a flange beam. But here what we do is we separate the beam so that the beam depth may be a little higher. We have to increase the height of the beam, but we can design it as a rectangular beam. So at all these locations, we have a separation and a continuous slab, and we can make the concrete sloping as well. Don't have to do it flat. So we can drain as well, drain easily as well. So we can have a slab which is free to expand and contract. So that's a possibility for the roof slab, so that you can have an accessible slab that can be used for mounting solar panels, or even having a greenhouse. Whatever the activity, it's possible to have a slab that is free to expand and contract, so that it will not induce any cracks in the walls. So that's another aspect that is possible to consider, especially when you go up to about 3 to 4 floors. So these are the various aspects that we have to consider when doing this type of construction, where our aim is minimize cost of the structure, minimize cost of finishes by improving the quality of block work, improving the quality of masonry. And then we are also interested in minimize the number of operations. So that's where I told you that when we are laying this, because we are doing only a thin concrete, 45 millimeters, we can do it slowly and make it a good finish so that the tiles can be laid directly on this. So those are all different possibilities of this method. And the other important thing is this can be designed for Europeans. Though it was initially developed for British code, you can design it for Euro codes as well. So if is that all clear, Bandhuga?
Yes, that is clear, sir.
Right. So basically, if you look at the concept, it is based on saving materials needed by the walls, minimize the weight of slab. Number 3, shear loads with frame and walls. So with 150 millimeter walls of hollow block work, we can go up to 4. Can we go up to 4? But you might ask, can't we go for a higher number? Then the answer comes with 200 millimeter hollow block. So the answer comes with that because this, when you use 200, the slenderness effects will be less. Yes. So you can see the capacity reduction will be lesser. And because the wall is thicker, it will have a higher capacity to carry the loads. So there can be certain advantages, but even 4 stories is a significant achievement because you can save a lot of cost needed for the completion of the structure. So that's how, that's a method that we developed as the answer to the escalating costs of construction. So already we have few buildings that we have completed. So we would like to see that more and more engineers trying this type of hybrid systems so that significant cost saving can be achieved. So, any specific questions, Panduka?
Up to now, there seems no questions. If you have any questions, you can either put in the chat box or can ask by unmuting yourselves.
Yeah.
Thank you.
Because what I thought was, we have covered lot of materials. So bringing this lecture series to an end, because the main theme was hybrid, lightweight, hybrid multi-story construction. So I have showed how to do the design on the masonry aspect as well as on the reinforced concrete. So what we thought also, bringing this lecture series to an end with this lecture, so that we can start a new series after a little break on a different topic, like how to design foundations, so some topic like that.
Okay, so there's one question, hand
Yeah.
raised. Engineer,
Yeah.
you can ask.
Good evening, sir.
Yeah, what's the question?
I was thinking now, we are doing hybrid designs to basically reduce the cost and reduce the material usage. Now we are using Euro codes or even British codes for the safety factor. Maybe the calculations are there for the UK, but the safety factors are being used for Europe and even UK or even Australia, USA. But considering the economic situation and the current context of the country, is it possible for a country like us to alter the safety factors, maybe keep the seismic safety factor and the seismic load as the same, but other factors, if we can think about, like without thinking long-term construction, if we can reduce the lifespan of the construction, and then think of reducing the safety factor, will there be an economic benefit as a nation?
No, actually, I think the thinking should be in the other way. Because if you look at now, when you have an economic crisis, we have to see how we achieve the economy. Now, one way of achieving the economy is improving the quality. Because if you look at the amount of material going into a block, the size of the block remains the same, and most of the costly materials will be sand and the small aggregates that are used. Those also will remain the same. So the only ingredient that you need in a little higher quantity will be the cement. But if we use proper quantity of cement and achieve a high strength block, then you can see with a block having a lesser width, we can actually go for a number of stories. So what I suggest is, the change in Sri Lanka that we need is actually in the side of quality, improving the quality of material and improving the quality of construction. So that's where we can see a lot of savings in material. So if you look at the way that normal construction is done, most of the masons, they pay very little attention to the quality. And even the verticality, all those things, they pay very little attention. Whereas, what we need is improving the quality of construction. So when the quality goes up, we will find that, the number of, on one side, number of operations can be reduced to complete the building. On the other side, we can use lesser amount of material to achieve the required strength. So what I see is, the correct way is not to think of altering the codes, because codes have certain factor of safety based on a lot of research. But the easiest thing we can do at the moment is improving the quality of construction. That is, that will allow us, even in if you look at the Euro code, if we can assure high quality construction, instead of using a factor of safety of 3, we can use a factor of safety of 2.6. So all those things are allowed in the Euro. So so the correct approach at the moment would be to concentrate on improving the quality of construction than, improving the quality of, reducing the factor of safety. I think we can achieve better economy by improving the quality of construction and not only the quality of construction and quality of materials. So those are the two things we should be concentrating at the moment. That's my opinion. Have I answered your question?
Clear, sir. Yes, sir. Clear, sir. Yes, it's clearly answered. Thank you.
Right. Because, trying to change the factor of safety is a too risky business. Whereas improving the quality can be achieved in a far better, much easier way. For example, even in a construction of a house, I mean, we can make a saving in cement by using an admixture while achieving a higher quality. So the cost might not vary much, but the strength will improve. So even for concrete construction, we have to think of improving the quality by using admixtures at the site level. Because generally, the use of admixtures is, people consider it only when they think about ready-mix concrete. But even at the site level, when they are mixing concrete, the admixtures can be used. So that way, we can improve the quality of construction. So I think the way forward would be to improve the quality of construction. For that, actually, we have to train the people. We have to pay a lot of attention and work with the people and help them to improve the quality of workmanship. Because, most of the time, very little attention is paid to the workmanship. So I think we'll have to, have some interest to improve the workmanship of the laborers, because, at the moment it is not very high, and there's a lot of room for improvement. So I think that is one area that we can concentrate as professionals. Okay.
Okay, sir. And sir, there's one other question.
Yeah.
What about the stability of wall and roof during either cyclone or tornado time?
And so basically, you can see in this construction, the concrete frame also goes to the top level. If I show you the kind of drawing that I have made, now here you can see all these are concrete frames. All these are concrete frames. So basically, what happens is, if you look at the uplifting associated with the cyclone, it will be something like 1 kilonewton per meter square. But if you look at the weight of this slab, that is 0.09 into 25, and that will be over 2 kilonewtons per. So you can see there's no way that the slab can be uplifted by a cycle. And because we have these frame also as part of the structure, the chances of any stability related problems would be minimal. So that's how you have to look at it. Is it clear, Bandhuka?
Yes, yes, sir. That is clear.
Right. So
And sir, there is
basically, yeah, this will be far better option than roof. Yeah. What's the question, Bandhuka?
the other question is how will be, I think we discussed this during one lecture, how will be strength reduction or any concerns on the electrical conduits or piping through the wall?
All right. So in that one, you know, where you have to actually now there are two options. One is, you know, now one place where you have problem is washrooms. So washrooms will be something like this, and you place the concrete, and then the other slab will come at a higher level. So the side difference will be about 200 millimeters, because you know we are dropping about here, we are dropping 200 millimeters, which allow us to have all the pipe work within this space. And then we can take it either through the slab or through the wall to the outer wall, or we can have a shaft to carry all the services. So because this allow us to make a drop of 200 millimeters, here of course you have to fill it concrete when you are doing the slabs. So what you do is you fix a timber plank, and because this slab is supported, we can fill the concrete when this concrete is done. So basically we can minimize the need for any horizontal chasers in the walls, because you know most of the plumbing work can be kept as vertical as possible. So because in any load bearing wall, we should not have chasers in the horizontal direction. That is not a good practice. So we have to plan the services in such a way that we keep most of the chasers as vertical as possible, because the effect of a vertical chase on a wall is minimal. So it will not be a major problem. Only thing is you have to carefully plan the services, because if you don't plan the services, then it will be the freedom to have the services is slightly restricted, because we are having a load bearing masonry system. But if you plan it, you know, you can keep all the chasers vertical, then there's no issue. Is that clear, Bandhuka?
Yes, yes, sir. That is clear.
The most important thing is, you know, dropping the slab of the washroom by 200 millimeters. That you can easily do in a load bearing system. So that, you know, most of the plumbing work within the washroom can be done. The horizontal plumbing can be done on the floor, and only the vertical ones can be taken along the walls. So that's the strategy that you have to use. Any other question?
For now, those are the questions. No more questions in the
Right.
chat box. Yeah.
Okay. So, in that case, shall we wind up, Bandhuka?
Uh-huh.
So this will be the last lecture on the series, but because we have covered the main theme, but we can have another series later.
Sure. Okay, yeah, okay, sir. We
Yeah.
will notify those information through our WhatsApp group and through
Yes,
ISL
yes,
mails as well.
yes.
And I would like to invite Vice President ISL Engineer Mrs. Kamala Gunawardena to have a vote of thanks. Over to you, madam. I think she's unable to connect due to some technical issue.
Yeah.
Um, so I would like to have if any participant is willing to share their ideas on this lecture series. If anyone is there. Okay. Thank you very much, sir. Actually, we are now concluding 16 lectures. Actually, last year for the whole year we had only 17 lectures for the structural design of highway bridges. So by the end of March, we are completing 16 lectures in this lecture series, and I think we got many positive feedbacks and positive responses from most of the practicing engineers in the field on this lecture series. Actually, it's like introducing new technology to the industry. So I believe that those who participated for this lecture series will bring this message to the industry and will engage in raising up the this crisis as I mentioned during the lecture series. So we are highly grateful and thankful for Professor for highlighting these areas, especially about these value engineering aspects and how our thinking pattern should be changed for to match the current situation. So we are so lucky to have this vision from this lecture series. And thank you very much for that. And we hope to continue the same lecture series in future uh, after some break. So we will notify all the participants about our next lecture series. And also I would like to thank all the participants who joined this lecture series throughout from the beginning up to today. Actually, from last 2 years, there are some participants who has joined with this lecture series. Actually, this type of lecture series started in Civil Engineering Sectional Committee when Professor was the chair in Civil Engineering Sectional Committee. Professor himself introduced this lecture series, and it was a great start because we got more engagements from participants with ISL. Because of this lecture series, many members joined this lecture series and ISL activities as well, as Professor started this type of knowledge sharing sessions, I think 2 years back. And then Engineer Mrs. Kamala Gunawardena, who was the last year chairman of Civil Engineering Sectional Committee, continued the same trend with Professor. And this year also, with the guidance of Civil Chair, Sectional Committee Chair, Engineer Mangala Silva, he also gave full support in continuing this lecture series. So thank you very much for all the participants as well for your enthusiasm and great questions, which made this lecture series a very successful one. And also, I want to thank the ISL Secretariat, IT department, and the publicity department for making those flyers and everything and arranging these Zoom facilities and hosting arrangements. So And sir, we would like to have one physical session as well. We will see in next few months, no, sir?
Yes, of course, we
Okay,
can.
okay, sir.
Okay,
And
Bandhu.
thank you very much, sir. Thank you
Thank you
very
very much.
much.
Thank you very much for everybody who participated. And your participation is the one that kept us going. Thank you very much.
Okay, thank you very much,
Okay,
sir.
Bandhu. Yeah, thank you.
And dear participants, that Vice Engineer Mrs. Kamala Gunadhan had shared some Google form which you can fill for any ideas or suggestions for our next lecture series. Kindly fill up that also. And we will share any more information through our WhatsApp group, and you also can share your suggestions through the group. Thank you very much, everyone. Thank you, sir. Good day.
Thank you very much. Thank you.
Okay. Yes.